Our next speaker is Dr. Bruno Basso, University Foundation Professor, Department of Earth and Environmental Sciences at MSU. His research focuses on integrating remote sensing technologies with crop simulation technologies to enhance water and nutrient efficiency and the sustainability of agricultural systems. Dr. Basso's talk is titled, "How are the plants doing? Ask the drone." He'll focus on how researchers are using drones to measure plant health, nutrition, and water, and how drones can improve food production and enhance the efficiency of water in agriculture. Please help me welcome Dr. Bruno Basso.
It is truly a pleasure to be here this afternoon to share some of the advancement in science and technologies that have occurred over the last few years to improve food production and the efficiency of resources. It is also a privilege to be on this stage with distinguished speaker and the Water Prize of 2016, Joan, a good friend of mine. So thank you for coming. It is important to provide a slight background on where we sit and the challenges that we face. We have a global food and water paradox. Often agriculture has been not receiving the right amount of attention. We give food for granted, despite the fact that there's still, 1 billion people undernourished with low nutritional values, food, and so on. So the phases that we face in agriculture are enormous, and this research and the things that I'll share today go towards that direction to improve the sustainability. Envision has both profit for farmers, but at the same time reducing environmental impact from agriculture to build a long-term resilience of agricultural system, to build the resources that we are basically reducing to a very low conditions, and we're only leasing the land. So we want to make sure we leave a sufficient amount of resources for the next generation. The paradox is really feeding more people with less water than we have, with the challenge of increased variability in climate. I did not include with less land. It is a little bit more complex aspect to explain in a few minutes, but we are, just briefly mention, we are losing the best land to urbanization. At the same time, there are new land coming into agriculture because of deforestations, and the problem, and in the end, those new lands are not necessarily, they don't have a suitability for agriculture. Then in the end, the sector gets blamed, and it's really for a poor decision rather than, the sectors per se. So agriculture has been around for the last, 10,000 years, and it has really allowed us to sustain our life on this planet, and we have to continue to do that. Just to put my talk in the context of the United Nations World Water Day, let me provide some facts on water in agriculture. So 70% of the fresh water is used for agricultural purposes, which is just the number. I can't understress how big of an amount that is, and because of that, we really have to improve the efficiency of using resources in agriculture. Even though 18%, only 18% of the cultivated land, which is 34% of the planet, but 18% is irrigated with an amount of 280 million, and 200 million hectares are in developing countries. So irrigation provides about 40% of the world food production, and about close to 60% of the cereal production. The United Nations Food and Agriculture Organization projected that there will be a significant amount of new land going in irrigation. And the bad news is that it is going to go in areas where there is not necessarily water availability. So this is briefly a map to show that the scarcity, and even in our own places here in the US and our nation, we have areas which are dominated by agriculture, which are in the orange spot, in the physical scarcity, which means that we are using resources at a rate much greater than what we can refill our aquifers. The purple areas where most of the food production needs to occur in the future is really non-accessible because of an economic threats. There is plenty of water. Those are close to the tropics, but it's really hard for other reasons. So we're all aware of the critical role of water in agriculture, and for food production. Food is extremely important. Both the quantity provides nourishment, but also the quality. I just want to say, as you probably can tell from my accent, I'm originally from Italy. So I grew up in the city of Naples, where people are obsessed with food quality. And when I came here, I had to adjust myself to the local the delicacies, and I have done that plenty, but I'm still working on the bun. So the amount of water that is used in agriculture needs to be seen as a water footprint. So in this case, every time we eat a hamburger, we have 2,500 liters, so 660 gallons of water that went in to produce that hamburger. Now, the colors there, the green water footprint, it's a good news. So if the amount of food that went to feed the cow just came from rain, it's not obviously as bad because it's green. It rained, and so we're using that water efficiently. But if it is from irrigation, has the majority, as you've seen, 60% of the cereal production, it's irrigated, then it's the blue footprint. Same thing applies for coffee. We all enjoy coffee. Every time we drink a cup of coffee, you have 70 liters of water going with it. You don't feel it, but psychologically, that's how it goes. This is the all green water because it's just coffee grows in tropical areas where it rains a lot. And one of the things that I'm interested in conserving over time is red wine, and 90 liters of water for a glass of wine. Most of the water used in this is rain-fed, so the majority, unfortunately, a greater portion of the grapes grown in California are irrigated, so there is a strong component of blue water in here. The good news, again, of the research, trying to kind of balance, the challenges with some of the advancement, is that in the case of a crop that we're more familiar with, corn, the efficiency in using water, the same amount of water. We used to produce 7.5 bushels per inch of water. Now we produce 27, close to 30 bushels per inch of water. So nearly 4 times, and that's due to improved genetics, but most of it improved agronomic management. Be able to produce more crop per drop is the goal, the mission of the agronomic research. So where do the drones come in? You're all waiting for drones. They're standing here. You can see 2 models. They fit in this larger new way of managing technology on the farm, goes under the umbrella of precision agriculture. We now have tractors that can drive themselves. Google and Tesla have been talking about self-driving cars. We have self-driving tractors since 20 years. I don't think that made the news very much. Obviously, there is the chances of hitting someone in a cornfield is much, much less. So this became possible because GPS was allowed to be used for civilian purposes, and by the elimination of delusion of precision. The military imposed the delusion of precision, so the point was never the correct one. It was very, many meters away from it. Now it's precise to basically the millimeter, sub-inch, and so on. So tractors can drive completely autonomous by themselves, and you don't have the overlapping or areas that they were uncovered, which was one of the major sources of inefficiency in using, products, inputs in agriculture. So it's extremely precise. So drones provide the similar type, so you have sensors on the ground, but you also have sensors in a continuum manner to be able to collect information on the planes. We also learned that planes are our best friends. We use them as our indicators. We'd rather use them than point-based sensors because they tell a lot more. So we have 70,000 plants of corn in 1 hectare. And there is a valuable information that they can provide just telling us, and we also learn that they don't mind us spying over them when we fly with the drone. So this, all this technology integrated has really allowed us to understand the spatial and temporal variability and be able to provide a prescription. Basically, what is the best way to apply this input, respecting the planned demand rather than one single blanket application. So even though this is really a public and general kind of talk, I'll try to make this simple because it's critical for you to understand how these drones collect information. And it is based on a physical principle that plants reflect the light in the green band. And so as you see there in the graph, the green band of a healthy plant, it is darker green, so it is not as high if the plant is unhealthy. So a lighter green, closer to white, as you can see when a color is white, when all the reflectance is reflected back, and you see a black when it is all absorbed. So when we see reflectance for the same pixel in a field, and compared to the next one, they have different reflectance. Each of them informs us about a behavior. So if we see plants reflecting more in the green band, that means that other pigments, carotenoid, chrysanthophyll, are going over the chlorophyll, and it's an indication of a plant not being healthy. So the cube here, as you can see, you'll see a thing blue if it is very low reflectance, 0 in the green and 0 in the red, and vice versa. So the combination of these 255 possibilities multiplied by the 3 colors allow us to create vegetation indices. We convert them into vegetation indices that allow us to back correlate the amount of chlorophyll, the amount of water in a plant. So one of the sensors that is not shown here, it's a bit further in the electromagnetic spectrum, is thermal imagery. Thermal imagery really measure physical, temperature. So said earlier, if a plant runs a fever, it's the first mechanism of showing unhealthy behavior. And thermal helps in detecting 2 things, is the presence of basically water stress or diseases. So the optical component of the sensors that have different ones. Before I move into those details, I wanted to show that the scale of our work goes from a point-based within the precision agriculture to a much larger, because the goal of my program and in general of the agronomic sciences is to be able to transfer this technology and not just learn from a single field that doesn't necessarily transfer to another. So we work on establishing procedures. So what you see here, it's really the earth breathing and dying, in weekly changes of the indices that I just mentioned, of vegetation indices and DVI, and the changes you can see from northern to southern hemisphere. So this kind of work is also part of a program where we compare the sizes and the scale of the information. So the drone that we have, a small fleet, we mainly use these 2 types. We have another one more sophisticated that hasn't reached our lab yet. But they're equipped with sensors, the digital video cameras, multispectral laser scanner that detects 3D and plant height with a very high resolution. Like any robotics, we also have our down moments, when we see them crash. We're doing better and better thanks to, the people, the very experienced crew over time have learned a lot, and they have to get a permit. They're basically a pilot, and that's another experience I wanted to share. Over time, the regulation have been so hard. Likely they have eased up. We had to take Greg Putner is a student in our lab that became a pilot. I made sure he promised that he will never become a Delta pilot because the technology that he learned during the exam, it didn't apply to, to large planes, but it's very, we had to deal with passengers, very unrational. But now we really can fly freely over agricultural fields and detect all this valuable information. So once we collect information, the point I really want to make is not that we fly the drone, it looks cool and it's all great, but the value is really in transforming first noise, data, information, knowledge into solution. And we've been successful in doing that because some of this work has been licensed out to commercial companies that implement it on a larger scale. So once this is the results of the analysis of the drone, it's not just even the image of the drone, how much nitrogen is being taken up by the plant, converted into an analysis that shows area that consistently lose nitrogen versus area that even provide excessive in terms of mineralization. So we are basically the doctors. We prescribe the amount of inputs that should be varied over space and time. And that's the ultimate goal of efficiency, both in terms of fertilizer, as in this case. We can do it for variable rate irrigation, provided the right amount. This is a collaboration that we're doing with a colleague of mine, Paolo Sabatini, in the Department of Viticulture, with the Gallo winery, a very large winery interested in using variable rate irrigation. They started on their own. We're collaborating to include more of a system approach. So all this information, as I mentioned, they go into a larger system, which is a crop simulation model. He was actually started here at Michigan State, but a professor retired now, Joe Ritchie. The model, the original model series was really designed to predict how much wheat was produced in Russia during the Cold War. I've taken on that work by including spatial and temporal variability and the importance of management to understand how much carbon we can store in order to improve the long-term sustainability of the system. And that combination allows us to have this type of prescription. The one other thing to underline the system is that one example in this case is different hybrids, different varieties. And so that is not Photoshop. It's really the combination of different cultivars with different level of greenness. And so this does not satisfy just the performance, but also the heart of the farmer, in this case, a true loyal Spartan. So the technology has really reached a level that has been technology, and the engineering has really been ahead of the game. The good news is that the science behind, which is, it deals with a much more complex system because the soil-plant interaction is really complicated, it's dynamic, but through the integration of information collected at high resolution through drone technologies, scaled up through satellite, and then accounting for the temporal aspects of including the impact of weather, climate variability, simulation of extended drought period versus waterlogging. All this integration has allowed us to reach solutions that farmers can implement to reach this goal of more sustainable agriculture. Again, underlying profit. If there is no profit for the farmer, the technology is not adopted. But our goal, what we have at our heart, is again the legacy that we have, be able to quantify the nutrients and the amount of time they stay in the environment, to be able to build that resource base that our next generation needs it. So I always use these sentences to producers and farmers, which are great people, very interested in their great stewardship of the environment. And we really have to thank farmers. Food production is in the end of very, very few people. And lots of people, as you know, leave the farms to go in the cities, but we're still able to produce a significant amount of food. We will continue to do so in the future with the help of technology, but it has to help them to make profit and at the same time, protect the environment. So I would like to conclude that obviously this work is not possible. It's very much of a team effort without the collaboration of the people in my lab. The list obviously very incomplete, many collaborators, and obviously if it isn't for the funding sources in having the visions of the critical roles of these aspects of research, we would not reach the long-term sustainability that we all hope for. Thank you very much indeed for your attention.
Going back to the MSU in the field, can you explain that again just a little bit?
Surely. It's just the previous slide. As you know, plants have chlorophyll and they are a different level of greenness. So the darker the helmet is planted with a different hybrid, so a different cultivar. That in this case is shown as an example, but now farmers apply different hybrids depending on different conditions that they are in the field. So if you have an hybrid that it does better in a sandy soil and behaves with a higher performance, then they're planted differently. Not just, this is just a simple example, varieties, but also the number of seeds per square meter. So you could have areas where you can have 3 to 4 if they're more prone to water stresses, and others where the same seeds that you don't apply could go in areas where there is more of a response. So we work on designing that prescription map. Here we're designing the helmet, but the farmer has implemented that on his own just to show that that was possible to the level of precision as well as accuracy of centimeter scale to reproduce that helmet.
Do you believe that increases in water efficiency is all that is necessary, or are there also other steps that need to be taken, like lifestyle changes and decreasing demand for things like the hamburger that takes so much water?
Yeah, obviously very good question. I feel that question requires pretty complex sorts of explanation, but let's say within the biophysical aspects, it's our job as agricultural scientists to be able to produce more crop per drop, and so that's the goal. Now, the land is really strained, and by changing in diets, as you know, China, all the kids in China are much more used to eat meat compared to the previous generation, and meat consumption has increased exponentially. So there are projections that if the consumption of chicken continues to be the way it's going in China, all the Midwest corn will be needed to feed the Chinese chicken. So that is something that requires a significant amount of both education and policy. The other way to look at it is like we went through that, the Western world went through that. It's almost a natural behavior that they have the possibility to do it, and they do it. So now it requires a social integration of understanding the strain on the environment that this type of diets impose. But we work closely with policymakers and the social scientists. But again, our goal is we still have to reach that goal of increasing productivity. Same thing is population increase worldwide. I mean, there are many different other solutions to be able to reduce that component of the pressure on the environment. But those are aspects that belong to almost other sciences.
Dr. Basso, thank you so much.
Thank you for having me.
Thank you.
Thank you.